Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain how to draw the bending moment diagram for a beam subjected to point loads. Let me explain the bending moment. Bending moment at any section is the moment produced by all forces on one side of the section which is trying to bend the beam at that particular section. If you are taking a section here, these forces are producing a bending effect. What is the resultant bending effect produced by all these forces with respect to this section is the bending moment. When you are taking a section, the bending effect produced by all forces on one side of the section will give the bending moment. If you are calculating the bending moment at a section somewhere here, if you take up these forces, it will produce a moment, summation of this moment, that is this 32.2 kilonewton will produce a moment with respect to this section, and 20 also will produce a moment with respect to this section, but they are opposite in direction. This will produce a clockwise moment, this will produce an anti-clockwise moment. Now the resultant moment, say m, and if it is clockwise, if you consider the right side forces, they will also produce a moment, and the summation of these moments will be counterclockwise and will have equal magnitude. If it is clockwise m, from right side it will be counterclockwise m. So this portion of the beam is subjected to a bending like this, from left side clockwise and right side anti-clockwise. So they will be equal opposite. So you can either consider left side forces in summing up the moments or right side forces. Both will give the same value of bending moment. So to calculate the bending moment at any section, you have to sum up the moments produced by all forces on one side of the section. Now let us calculate the bending moment at point B. At point B, if you consider the left side forces, there is only one force, 32.2 kilonewton. This will produce a clockwise moment. Okay, 32.2 into 2, the distance. Since we are calculating the moment, so you have to multiply with the distance. So 32.2 into 2 or 64.4 is the bending moment produced at point B. So 32.2 is producing a clockwise moment, and there is no other force. There is one force here that will not produce any moment with respect to point B. So bending moment at point B is 32.2 into 2 or 64.4 kilonewton meter. That is a bending effect produced by this force with respect to this point. So you can see here, so this is 32.2 into 2, so that will give 64.4 kilonewton meter. From left side, when you sum up, when it is clockwise, you will take positive bending moment. So it is producing a positive bending effect. So you are getting the bending moment as 64.4 kilonewton meter. Now this is a force acting at point B, and apart from that, for equilibrium, when you consider, there will be a shear force at that section and also bending moment. Bending moment, this is a resisting couple or resisting moment formed at that section. So at that section there will be a resisting moment and resisting force which is imparted by the other part of the beam. So remaining part of the beam, this part of the beam will be exerting a force at that section and also producing a resisting moment. So that is nothing but the shear force and bending moment. So this is also producing a same bending effect. Right side forces also will be producing the same bending effect, and this will be producing a shear force 32.2 minus 20, that will be 12.2, and right side forces also will be producing the same amount of force downward, so that the net force will be 0, and this will be producing a clockwise moment of 32.2 into 2, 64.4. From right side also will have same, right side forces will produce same amount of moment but in the opposite direction. So this resisting moment and resisting force can be considered as bending moment and shear force. So to calculate the bending moment at any section, you have to only sum up the moments of all forces by taking clockwise positive when you consider the left side portion. Clockwise positive. So this is producing clockwise rotation with respect to point B, and the moment produced by this force is 32.2 into 2 or 64.4 kilonewton meter. So that is the bending moment at B. Now let us find out the bending moment at C. Now bending moment at C you can find out as 32.2 into 7, that will be producing a clockwise rotation with respect to point C. So I am taking section C and considering all forces on left side and summing up the moments of all that forces with respect to C. So 32.2 into 7, which is producing a clockwise rotation with respect to C. So take that as plus 32.2 into 7 plus. Now 20 is producing an anti-clockwise rotation with respect to C. So 20 is producing an anti-clockwise rotation. So it is 20 into 5, and that is minus 20 into 5. And that summation will give the bending moment at C. So RA, that is reaction at A, that is 32.2 into 7 minus, this is anti-clockwise moment with respect to C, minus 20 into 5 is equal to 32.2 into 7 minus 100. You will get 125.4 kilonewton meter. That is the bending moment acting at C. You can also consider the right side force and sum up the moments. 41.8 into 3, that will also give the same value, but when you take from right side, that will be counterclockwise with respect to C. This force is producing counterclockwise moment, so counterclockwise should be taken as positive to get the same sign convention. Okay, so you don't consider the right side forces, there you have to treat counterclockwise as positive. So when you want to find out the bending moment at any section, sum up the moments of all left side forces by taking clockwise as positive, anti-clockwise as negative with respect to that section. Now let us take a section at a distance x. The bending moment at this particular section will be 32.2 into x. That is the moment produced by this 32.2 kilonewton force. 32.2 into x, that will produce a clockwise moment with respect to this section. Okay, and this 20 also will produce a moment, but it is anti-clockwise, but the distance is total distance, this is x, and you have to subtract 2. This distance is 2 meter, so if you subtract 2, you get x, total x minus 2, you will get x minus 2. So 20 into x minus 2, that will be a negative moment. It's producing anti-clockwise moment with respect to this section. So minus 20 into x minus 2, that will be the bending moment at this section. So bending moment at a distance x is 32.2 into x clockwise moment with respect to this section, so positive. This is anti-clockwise moment, so minus 20 into x minus 2. Now this you can reduce into 12.2, 32.2x minus 20x, which will give 12.2x, and minus of minus plus 20 into 2, 40, plus 40. So finally you can write thus 12.2x plus 40, that is the bending moment at this section. Now x I have taken as a variable, so x can be here, somewhere here, immediately right of B. Immediately right of B also same forces are there. and if you move up to C, also these same forces are there producing a moment, but you cannot take x less than 2. If you take x less than 2, these forces are not coming, and this equation will not be valid, because we have considered both the forces 32.2 and 20 in writing this equation. So x can vary from 2 to 7, and not more than 7 also. If it's more than 7, you need to even consider this force. So the value of x can vary from 2 to 7. That will give the bending moment at any section in the portion BC. At B also you can calculate. If you substitute x as 2, then it will be 24.4, 12.2 into 2, that is 24.4 plus 40, 64.4. that you already calculated bending moment at B as 64.4. Now bending moment at C also you can calculate by substituting x as 7. So that will give bending moment at C. So any distance you substitute between B and C, that is from 2 to 7, x is 2, it's here, and x is 7, it's here. So that value if you substitute, you will get the bending moment. So this is valid only for the portion BC, or anywhere between B and C. This equation for bending moment is valid. You can calculate the bending moment. But we don't need this equation right now. It's only I have written this equation to explain the nature of variation of bending moment in this section. So it is a linear variation, or it is a straight line equation. This bending moment equation for that section is a straight line equation. So bending moment is varying linearly, or you can show the variation of bending moment in this portion BC by a straight line. So here we have calculated the bending moment at B as 64.4. Now at C you got 125.4. So from 64.4 to 125.4, that variation is going to be linear variation, straight line variation. So that variation you can represent. So any section you take, when point loads are acting between 2 points, then the variation of bending moment has to be linear. Now if you are considering in the portion AB also, it is going to be linear variation only. Bending moment is going to linearly vary with respect to distance. As you know, bending moment is force into distance. Moment produced by this force. If it's in the section AB, bending moment is moment produced by this force. So if x is less than 2, then you will get 32.2 x. Okay, so that is also straight line equation. Okay, so for the section AB, the bending moment equation is 32.2 x. There x value can change from 0 to 2. Okay, so you understood that variation of bending moment is linear in the section AB or section BC, even section CD, the bending moment variation is going to be linear. And bending moment at A is going to be 0, since there is no force on left side. Only one force is acting at A, and that will be producing 0 moment with respect to point A. Now bending moment at D, if you take all these forces, if you sum up, it has come summation of all forces acting on the beam, including this force. This force is producing 0 moment. So it is nothing but the summation of all forces on the beam, and that has to be 0. So bending moment at D will be 0, and bending moment at A will be 0. Only at B we got 64.4, C we got 125.4, and we know the variation of bending moment. Okay, here it is 0, you get 64.4 here, and here 125.4, and the variation is linear, and 125.4, here it is 0, the variation is linear. So you can draw the bending moment diagram. So the bending moment diagram, you can show the variation of bending moment. So from 0, the variation is linear in all the sections because point loads are acting, no other type of load is acting. So the variation you can show linearly variation. So bending moment at B is 64.4, bending moment at C is 125.4, and the variation you can show linear variation. So this way you can show the variation of bending moment along the length of the beam. So that will give the bending moment diagram. So entire beam is subjected to only positive bending moment. Any section you take, bending moment is positive, but bending moment is continuously varying in all the sections, and it is the variation is a linear variation. So this is how you plot the variation of bending moment. So we need to calculate only at the salient points bending moment, and we will be knowing the variation based on the type of loads, and you can easily plot the bending moment diagram. Next I will explain the sign convention. Sign convention you already understood, but I will once again explain the sign convention used in the shear force and the bending moment calculation. Now sign convention used for shear force I will explain first. Let us take a small element in over the beam here. Okay, so this beam subjected to point loads. Let us take a small element. So I have shown. No, let us take this element. I have shown that element here. So in this small element I have shown enlarged. Now these forces is producing a shear force, and we know the shear force is 61.1 minus 31. So that will give 30.1. Shear force is upward. So okay, this summation is 31.1 upward. So you are getting a upward force here on left side of this element. Now if you take right side summation also, you get 52 is there, 24 is there, both are downward. So you get 76 downward and 45.9 upward, and this summation also should give the same magnitude of, that is 30.1, that should be downward. Okay, this is more and this is less, so the resultant is downward. So this way the forces are acting. So left side these forces are pushing the beam up, right side the resultant of these forces pushing the beam down. So this is considered as a positive shear force. So here if you take an element here anywhere in between B and C, that is subjected to shearing forces like this, from left side upward push and right side downward push, and that is considered as a positive shear. And as a result of this positive shear, the beam element can deform as shown here. So left side this may move up and distort the element, and right side this can move the fibers down and distort the element like this. So beam element, if at all, if it is deformed due to this shearing forces, the shear deformation will be like this. So this kind of deformation is considered as positive shear force. So positive shear force is the left side of an element if it's subjected to upward force, and right side of the element if it's subjected to downward force, it is considered as positive shear force. Now let us consider an element here. This will be subjected to forces like 61.1, minus 31, minus 52, minus 24. The resultant is going to be definitely a downward force. So there will be a downward force, that is a shear force here, and right side there will be an upward force, that will be 45.9, and left side summation also you should get 45.9 only, but it will be downward. Now the beam element if you take here, that will be subjected to a downward push on the left side and upward push on the right side, both equal forces but pushing it in opposite direction, and they are trying to deform the element. So the element, when it is subjected to downward push on the left face and upward push on the right face, that is considered as negative shear force. and as a result of this negative shear force, if the element deforms, it will deform like this. Left side the fibers will go down, and right side the fibers will move up, and this kind of deformation is considered as negative shear force. So this is a sign convention used for shear force. Whenever you find out the shear force at any section, when you take the left side summation, you should take upward positive, downward negative. If you are considering that section and calculating the shear force based on the right side forces, then you have to take downward positive and upward negative. Okay. Now let us see the sign convention for bending moment. Now the sign convention for bending moment is left side clockwise is positive, or right side if you take anti-clockwise is considered as positive. Now let us take the element here, that easy way to find out the bending moment. 32.2 into 2, that is the bending moment acting at B. Now I have taken in a small element at point B, at the section B. So 32.2 into 2, that is a bending moment acting. Okay, moment produced by this force, 32.2 into 2, it is clockwise, 64.4 clockwise. Okay, now if you take these forces, that will produce 54 into 5, that will be 270, that will be clockwise, and there is another moment produced by this force, that is 41.8 into 8, so that will be 336.4. So this is 270 and this is 336.4. Because they are acting in opposite direction, the resultant moment produced by these two forces with respect to section will be 64.4 counterclockwise. So from here it is clockwise, from here it is counterclockwise. So 64.4 clockwise and 64.4 counterclockwise. Now this kind of bending is considered as positive bending moment. Okay, and that is why when you take from left side, the clockwise rotation is taken as positive. So this force is producing a clockwise rotation with respect to point B, and that can be considered as a positive bending moment. If it downward force here will produce an anti-clockwise rotation, if it is there, that should be considered as a negative bending moment. This kind of bending moment will sag the beam element, and this kind of sagging is considered as positive bending moment. If a beam sags under the action of bending moment, that is considered as positive bending moment. Negative bending moment is just opposite. Left side if it is counterclockwise and right side it is clockwise, that is considered as a negative bending moment. And as a result of negative bending moment, the beam hogs. I cannot show a portion here because all elements on this beam is subjected to positive bending moment. So anywhere if you take, you will get only positive bending moment, or left side portions will produce clockwise moment and right side will produce anti-clockwise moment. So any beam part, if it's subjected to bending like this, left side counterclockwise and right side clockwise, that is considered as negative bending moment. And as a result of negative bending moment, the beam element will hog. So hogging of a beam section is considered as negative bending moment. So sagging bending moments are considered as positive and hogging bending moments are considered as negative. So this is a deformation of an element due to bending moment. That's all for today. Thank you for watching.